So I did make a mistake in my numbers here. So for the first one, for the tail approximation of e to the xy, the tail approximation is right up to this point. However, this number is not correct. I have 4.58030488, I believe is what I have when I did it again. And this number is still the same. And here as well, when I did this one, I think I didn't divide one of my numbers by 2, or more than one of my numbers by 2, and so I didn't get the right number here. I got 7.45 in this case instead of 6.4, so I have 7.45. This number is still 6.912. All right, so now that I've said that, I think we can go on to the next part. And hopefully that is now correct, and you guys are all going to agree and say, yes, Dr. Wesley, you are right now. Correct. And you weren't before, but you should be A-okay now. All right, so let's talk about deriving Runge Kutta. All right, so we want to do just the simplest one. We're going to derive Runge Kutta of order 2 is what we're going to look at. Runge Kutta of order 2. Deriving Runge Kutta of order 4 is very, very difficult. We're going to do the easiest one possible, which is Runge Kutta of order 2. So let's do that together. Before we start with Runge Kutta of order 2, right, let's just talk about orders method real quick. Orders method, right? And we know orders method is y sub n plus 1 is equal to y sub n plus h. We're going to put the h at the back. F of t sub n, y sub n times h. And we have y sub 0 is equal to y t0 is equal to y sub 0. Okay. So this is Euler's method. Okay. And when we look at Euler's method, what we're really using, when it comes down to it, is that we're using the derivative to help us approximate the next point. So here's our derivative. Now this is the derivative that we have when we have y prime is equal to f of ty, comma y of x0 is equal to y of 0. This is our initial value problem, right? And so we're using this derivative, this part right here, to help us approximate the next iteration in our solution, right? So we have, maybe we know this value, y sub n, right? And we want to get to y sub n plus 1. So what we're doing is we're using this derivative from our original differential equation to help us to get to the next point. So essentially we're using the derivative to help us approximate the next value, which makes perfect sense, right? When we're dealing with a differential equation, that we want to use the derivative to get to the next value of our solution. And what Runge Kutta does is it says, okay, instead of just using one derivative, right, to be able to do that, why not just use 2 derivatives, just at different places? Why won't we use this derivative, but we use that derivative at different places, and then we just add it together? We use a weighted derivative instead of just one derivative, a weighted derivative, to help us approximate the next value in our solution. So in Runge Kutta, we are trying to use the weighted average of the derivative f of ty at different points to get a good approximation of the solution. Okay. So we're going to use a weighted average. So what points are we going to use? What points are we going to use to get a good approximation solution of a differential equation? Differential equation. So what points are we going to use? And what weights? And that's the key here to this. We're going to use a weighted average. And for the Runge Kutta or method of order 2, we're going to use two derivatives. Well, we're going to use one derivative, but at 2 different locations to be able to come up with this weighted average. So we use weights, W1 and W2, and points. Ty, or T sub n, Y sub n, we'll just say Ty just and forget about the subscripts for right now, and T plus alpha H. So we're essentially going to perturb, so we're going to go a distance of alpha H away from T, okay, comma, Y plus. Here is where this gets interesting. We're going to have beta F of T, comma, Y times H. So our Y value, right, the Y value of this point is going to depend on what my derivative is at that particular location, Ty, right? So here, T, the next T value is going to be a fixed value of alpha times H, but the Y value is going to depend on what my derivative is at that particular location. So we're going to use these 2 points to approximate my my differential equation solution. And we're going to plug these 2 points are going to be plugged into my, essentially it's going to be plugged into my new method, which is going to take the place of what we have right here in Euler's method. So to determine the weights and points, we use the Taylor series. Of 2 variables on the equation. Here it is. I have y of t plus h is equal to y of t plus. Remember that y of t plus h is really y sub n plus 1. Right? Remember we talked about this before. Y of t plus h, I could really relabel this as y sub n plus 1. Y of t is going to be my y sub n. Okay? And then my inside here, I'm going to replace this guy with W1 F of Ty plus W2 F of T plus, in this case, alpha H, comma, Y plus beta F of Ty times H. Oh, the H should go. And then this whole thing, right, this is going to be my weighted derivative, this plus this, and then I'm going to have a times H on the outside, right? This part here is just my point that I have down here. Okay, times H. So essentially this thing here is replacing this right here in Euler's method. We just made our life more difficult, as you can imagine. Now we're going to use our Taylor series of 2 variables on this equation. Now where are we going to use this Taylor series of 2 variables on the equation? We're going to use it on this part right here. Can you guys see? I have t plus alpha h. I have y plus beta f of ty times h, right? So this is going to be my, if you guys remember Taylor series of several variables, I can really treat this like f of t plus ah y plus bh. Right? I'm going to do a Taylor series on this particular part right here. I'm going to expand this out. So using Taylor series, let's look at just this part right here. F of t plus alpha h, comma y plus beta f of ty. And you know what? Instead of me writing f of ty every time, can I just write f? Just to make our lives easy. So it's going to be t plus alpha h, comma y plus beta f times h. Okay. Just remember that f is a function of both t and y. You just kind of remember that as a kind of a fact. So let's just write out the first few terms of the Taylor series, if you guys remember. If we write the first few terms of the Taylor series, we get this. This is going to be f plus the partial derivative of f with respect to t, right, times ah, times alpha times h. Good Lord. Thank you. Thank you for your mercy and grace. Plus the partial derivative of f with respect to y times, now here my b is beta times f. Beta times f times h. Now if I wanted to, I can go to the second order derivatives, but I don't need that here. I'm going to stop right here. So I'm going to say, well, this guy is approximately equal to this. Okay. If I were to keep going, then it would be equal to it, right? If I let this Taylor series extend out for an infinite number of terms. So I'm going to just stop with these terms. And guess what? I'm going to plug this. I'm going to plug this back into my original function. So this, wherever I see this part here, I'm going to replace it with this in this particular equation I have here. So plugging the above Taylor series into the first equation, we get, what do we get? Y of t plus h. I'll be able to talk eventually, I hope, by the end of this video. Is equal to yt plus, no real excuses, but I've been sick this past week, and so getting over it. W1, I don't think I had the coronavirus, don't worry. Times f, let's just say f instead of f of ty, because I'm getting tired of writing ty every time. Plus W2 times, remember, I'm going to replace this thing with the right-hand side. I have f plus partial f with respect to t, alpha h, plus the partial f with respect to y, beta f h. I think I need another parenthesis. Okay, times h on the outside. And if I want to, I can distribute and collect some terms. So I can say y of t plus h is equal to yt plus, here I could say w1 plus w2 f, right? Because I have f in both of these two terms, w1 plus w2 f. Here I have w1. No, I don't have any w1. I have w2 times the quantity ft alpha. I just separate these two guys. So I have so many ways to do it. All of them are good. W2 times the partial derivative of f with respect to t, alpha h. You know what? Let's get the alpha on the outside too. Let's do it like this. So we have W2 alpha partial derivative of f with respect to t times h plus W2 going to the next term beta, right, times the partial derivative of f with respect to y times f h. All that multiplied times h. Deriving the easiest version of Runge Kutta. Now that we have this, we say, okay, Dr. West said, how in the world is this anywhere useful? I mean, why did we do all this? How does this help us with anything? Well, the thing is, now I say, okay, wait a minute. We know that our solution looks like this. Y of t plus h is equal to y of t plus all this garbage. But also, we know that I can write y of t plus h as its own Taylor series in terms of a single variable. A single variable in terms of just t. I can write y of t plus h in terms of just t. And what does that look like? Well, it looks like this. Y of t plus h is equal to y of t plus y prime of t times h, right? Plus y double prime of t times h squared divided by 2. Okay. So when we look at this, we say, wait a minute, these two things should be equal to each other. They should be equal. These two equations should be equal to each other. This equation and this equation should be equal. At least up to h squared. The reason why I say that is because I have an h squared, right? Can you guys see it? I have this h times h, that gives me h squared here. H times h, I get an h squared here. H times this gives me my first term h, right? So if we distribute this h through, we get an h term and we get an h squared term, just like we have an h term and we have an h squared term here. So these two equations should be equal to each other. They should be exactly the same, right? Because we're dealing with we're essentially talking about the same solution. We wrote this solution, this Taylor series in terms of two variables. We wrote this Taylor series in terms of one variable. But these should be equal to each other. They should be exactly equal. And since they are exactly equal, we can create this system of equations. So that's what I want to do next. Now, before I can create this system of equations, I need to realize what is y prime of t. Let's do something first. I'm gonna write something down here, but I'm gonna put it over here first. What is y prime of t? Now remember our differential equation. So our initial value problem. Our initial value problem was this: y prime is equal to f of ty. Y of 0 is equal to y of t of 0 is equal to y0. Okay. So y prime is really f. Okay. Y prime is really f. So if I wanted to, I can put it down there. I can say y prime is really f. I'm going to do that. This y prime that I see here, I could really just write it as f. Plus what? What's y double prime? Well, we have to figure out what y double prime is. Y double prime is the derivative of f with respect to t. Okay. Now, what is the derivative of f with respect to t going to be in this case, right? And here we have to use chain rule. We have to use chain rule. And chain rule says that what we're going to get is this. It's going to be the derivative of f with respect to t plus the derivative of f with respect to y times y prime. That's what chain rule says. Okay? So if I take the derivative of f with respect to the derivative of f with respect to t, right? The derivative of f with respect to t is going to be equal to this by chain rule because y is a function of t, right? You have to go back to calculus 3 for this one. But what is y prime? Y prime is really f. So it looks like this. So wherever I see a y prime, I can really replace it with this. F. Let's say f with respect to t plus the partial derivative of f with respect to y times f. All that multiplied times h squared divided by 2. Now I want you guys to notice something. You're like, well, Dr. Wesley, F, F. You guys see it, right? F, F. And then I have this H on the outside that's going to multiply times this H. So this is really FH, right? This is FH. I have an FH there. And what's in front of FH? I have W1 plus W2 is in front of this FH. So if these two things are equal to each other, then W1 plus W2 has to be equal to 1. I want you to think about that for a little bit. I know that this is a lot of stuff to keep in your mind, but I want you really to think about it. So this is really F times H, and I have an F times H here. If these guys are equal to each other, then W1 plus W2 has to be equal to 1. Okay? Well, let's look at the next thing. I have an FT, right? I have an FT H squared, right? Because this is H times H, I have an FT H squared. Here I have an FT H squared, right? Here in front of this FT H squared, I have W2 times alpha. What do I have in front of this F2H squared? I have 1 divided by 2. See, because there's a 2 right here. So really I have W2 times alpha is equal to 1/2. W2 times alpha is equal to 1/2. I want you to think about that for a little bit.